about that. How do we look to somebody else? Oh, these are some of those fusion reactions. Now, you got to be clever. You want charged particles. There are many different fusion reactions. And if they give you neutrons, they're a pain in the butt because they go out in all different directions. How do you get something useful in the way of propulsion out of that? You don't. But if you produce charged particles, we know how to accelerate charged particles with electric and magnetic fields. You kick them out that way, all of them. This is helium-3. This is heavy hydrogen deuterium. Helium-4, which is normal helium. This is a proton. This is the reaction we want. Now, MeV, that's million electron volts, and you say, what the heck does that mean? Well, a normal chemical reaction, burning a match, with gasoline in your car, so a few electron volts per reaction. You know, under 10, let's say 2, 3, 4. These nuclear reactions, 18 million electron volts. Now, we have already put that to use in the fission end of things, and I think I have some pictures. What I'm saying is, this is reality. It isn't science fiction. There's a nuclear-powered submarine. First one was launched in 1956, the Nautilus. Can go around the world underwater without coming to the surface. You remember during World War II, submarines could stay under, you know, a day or so, maybe the air got pretty bad. Around the world, underwater. Several hundred of these have been built on planet Earth. All the major powers. It's something Earthlings know how to do. You wouldn't know this from the ancient academics. There's my favorite use of nuclear energy. This is a nuclear-powered aircraft carrier. We have several. The Russians have, Chinese have one, I think. These things can operate for 18 years without refueling. 18 years. Think about that for a minute. They also set up the situation compared to flying saucers. People say, how could a saucer crash at Roswell having just come from another star system? Nobody says it did. You got a mothership, your aircraft carrier, if you will, which has one kind of propulsion system. It carries 75 little airplanes, which have quite another and can only operate for 1, 2, 3 hours without refueling. You have your Starship Enterprise, using, say, a fusion system, carries a whole bunch of little Earth excursion modules, which have to fly in a heavy gravitational field. You have the atmosphere to worry about heating and drag and all this other stuff. It's a perfect analogy. Nobody said the motherships crashed. There's some great sightings of huge motherships. 0.6 to 1.2 miles long. That's pretty good size. And people have observed little ones coming out of the big ones. Makes sense if you think about it. Hey, can you imagine operating for 18 years without refuel? I'll have to dig out a number. Somebody probably has one. How many tankers of bunker C fuel oil you saved in doing this? It's a lot. A big number. Oh, I just get a kick out of this. It's one of the Pioneer spacecraft, and it's got some radioisotope thermoelectric generators. And one of the early days of the space program, the noisy negativist said, hey, look, you're going to want to stay in touch. You put a man in space, you got to be able to talk to him by radio. But look at the weight of the power plant. Look, a radio station broadcasts at 50,000 watts, 100,000 watts, and that's just a few hundred miles. You want to keep in touch with one of these guys in deep space, that power plant, you never get it off the ground. The Pioneer spacecraft, I worked on that back in the early 70s. The transmitter broadcasts at 8 watts. Power of a Christmas tree light bulb. But it doesn't broadcast in all directions. It sends the signal via antenna back only toward Earth. In addition, we don't have a little rabbit ears down here to pick up the signal. We got a 240-foot diameter antenna. Very much greater sensitivity. It's still broadcasting. 40 years ago. And the source of the energy? A little radioisotope thermoelectric generator. Uses plutonium. Not the bad kind, the good kind. And has a long half-life. It'll still be broadcasting after all of us are gone. That's nuclear. Now you say, why don't they use solar power? Because the farther away you get from the sun, the less energy you get. Let's take advantage of nuclear. In our Canadian nuclear reactor, the fuel bundle this big, 44 pounds, produces as much energy as burning 400 tons of coal. That's 4 coal cars. This big. What I'm trying to say is we already know, we Earthlings outside of the university environment, know that there are ways to produce a lot of energy in a small volume, small weight, etc. We need to think about using them. So this was kind of neat. One of the few programs I've worked on that wasn't canceled before it came to fruition. Oh, one of the other objections. You couldn't stand the acceleration. Saucers are impossible. Nothing can move like that. Violates the laws of physics. The laws of physics don't tell you anything about what your body can stand. Good, sensible design. There's one book that says when you get to 9 Gs, you die. Yeah, if you run into a wall by being accelerated at 9 Gs, you're going to be smashed to smithereens. Yeah. This is to give you an idea that the answer to how much acceleration you can stand is it depends. For how long and in what direction with regard to the body. You ever notice the astronauts go up on their back? It's not because they're lazy, it's because you can stand a lot more acceleration back to front than foot to head. The joints just aren't set up for that. A trained pilot can perform a tracking task while being accelerated at 14 Gs for 2 minutes, which means absolutely nothing until I tell you that 14 Gs is an acceleration at 300 miles per hour per second. At the end of 10 seconds, you're going 3,000 miles an hour. At the end of the 2 minutes, you're going 36,000 miles an hour, and you're long since out of sight and off the Earth. This is measured data. You know, not walking around drinking a beer while this is going on. And you can't be 87 and just have had 3 heart attacks. And there are constraints to this sort of thing. You can stand, that's the 14 G mark. Actually, you can stand 30 Gs for 1 second. That's 0 to 600 miles an hour in 1 second. And there was a little rocket sled out in New Mexico that gave them a little more acceleration than expected. They got up to 620 miles an hour and stopped in 3/4 of a second. He took 43 Gs, and boy did his eyeballs hurt. He lived to die, I think he was 92 when he died. So you got to do things right. You got to recognize the limitations. You have to design them into the system. But pay attention to the people who do the work, the engineers of the world, not the academics. And the 3 different curves, it depends back to front, foot to head, front to back. You know, it's like how far can you carry a weight? Well, how big is the weight? You know, you can carry a small weight a lot farther faster than a large weight, can't you? It depends. Aren't easy answers. There's a whole new approach to propulsion, electromagnetic submarine. This was built and tested, successfully operated back in the mid-60s. No moving parts.